Pluto, a distant and puzzling world, was once a single honest planet, an individual from our planetary family. In any event, disturbing explanations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight. With astonishing receptiveness, they suggested that this chilly world is on a potentially loaded intersection with Neptune. But how could this happen? Moreover, what might be the results of such a tremendous event? Are we seeing a captivating anomaly, or is there something more to this approaching celestial encounter? Pluto, a former planet now considered a dwarf, was once thought of as a more modest planetary member due to its eccentric orbit. Yet it remains a subject of interest and focus in the cosmic community. According to consistent findings by leading experts, Pluto's path is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising alarms about a potentially hazardous collision between these two bodies, one that could even pose a threat to Earth. But is such an event truly possible? Pluto's journey around the Sun is unlike any other planet in our nearby planetary framework. It takes an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto hasn't even finished one full orbit. Pluto's orbit is highly eccentric and tilted at 17 degrees to the ecliptic plane, a stark contrast to the near-circular orbits of the larger planets. This inclination and eccentricity add layers of complexity to its orbital pattern. Perhaps most fascinating is Pluto's interaction with Neptune. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying expectations based on their usual positions. The answer lies in the gravitational influences of other planets. After Pluto's discovery, astronomers struggled to understand its strange orbit. Unlike most planets that orbit close to the ecliptic plane, Pluto's path stood out due to its sharp tilt and irregular shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's, yet they never collide. This is a testament to the complexities of celestial mechanics. The three-body problem in space concerns how three objects like Pluto, Neptune, and the Sun move and influence each other through gravity. It's like trying to predict where they'll go based on how they start and how they tug on each other. In Pluto's case, its orbit, Neptune's orbit, and the Sun's gravity all interact in a chaotic yet stable way. Terms like asymptotic libration, secular variation, and the VZK wobble are part of this dynamic. According to astrophysicists, what keeps all planets in their orbits is a kind of libration. In Pluto and Neptune's case, this means that whenever Pluto crosses Neptune's orbit, it is always about 90 degrees away in spatial position, preventing a collision. Degree libration, on the other hand, refers to the vertical motion of a celestial body within its orbit. For Pluto, this means that when it gets close to Neptune or any gas giant, it's typically far above the orbital plane, adding another layer of safety from potential impacts. Another crucial factor is the VZK wobble, named after scientists V. Vasiliev A. Zaslavsky and Y. Kuzmin. This wobble explains how gravitational interactions between Pluto, Neptune, and the Sun maintain the stability of Pluto's orbit over extremely long timescales. Despite how wild and unpredictable space might seem, certain rules and patterns help keep everything in order. This three-body problem is central to understanding how orbits evolve due to gravitational tugs. Studying this helps us better grasp Pluto, our neighboring planetary system, and even distant exoplanets. Numerical simulations in the late 1980s showed that despite these stabilizing forces, Pluto's orbit is chaotic. Small differences in initial conditions can lead to massive changes over time. Still, Pluto's orbit has remained consistent over long periods. Later computer simulations have revealed how gas giants like Neptune, Jupiter, and Saturn influence Pluto's orbit. Pluto and Neptune are in a 3:2 resonance. For every 2 Pluto orbits, Neptune completes 3. This resonance keeps Pluto's orbit stable. But Neptune isn't the only influence. Jupiter's gravity also plays a major role in protecting Pluto's path, and Saturn contributes as well. These simulations suggest that Jupiter alone could keep Pluto on a stable trajectory for billions of years. Together, Neptune, Jupiter, and Saturn act like cosmic guardians, ensuring Pluto doesn't run into trouble. These complex dynamics are essential to maintaining the order and balance of the solar system. Without them, bodies like Pluto might crash into others or be ejected from their orbits, triggering a chain reaction that could disrupt the entire system. For Pluto, especially with current discussions about a possible future collision with Neptune, understanding its orbit is crucial. It gives us a clearer picture of our neighboring planetary system's dynamic nature. Pluto's case shows how even the most unstable-looking orbits can achieve harmony through the intricate dance of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and analysis to better understand our place in the universe. Exploring the depths of space often confronts us with the unpredictable nature of celestial objects, and Pluto's orbit is a perfect example of this. The idea of orbital resonance, where a celestial body's orbit depends sensitively on its initial conditions, is clearly illustrated by Pluto. This means that even tiny changes in Pluto's position or speed can drastically alter its long-term path. Using computational simulations has been invaluable for understanding how Pluto moves through space. These simulations model gravitational interactions with extraordinary precision. By adjusting tiny variables, astronomers can see how even slight differences can make Pluto's future path diverge wildly. In the late 1980s, simulations revealed that despite stabilizing forces like asymptotic libration and degree libration, Pluto's orbit can still be wildly unpredictable. A tiny change in its starting position or velocity can result in a vastly different orbit over time. Yet remarkably, Pluto's orbit remains stable for billions of years, suggesting a hidden order behind the apparent chaos. These turbulent orbits present major challenges. The nature of these systems means long-term predictions are often fraught with uncertainty. Numerical simulations are powerful tools, but they also show the limits of our forecasts. Small errors in input can lead to major deviations in outcome. Pluto's chaotic orbit is a reminder of the ever-evolving dynamic universe. Despite our progress, Pluto illustrates how much we still have to learn. Understanding the gravitational effects of the gas giants on Pluto provides key insights into the broader solar system dynamics. It shows how every planet's presence and position can influence the stability and trajectory of others. Neil deGrasse Tyson, a renowned astrophysicist, offers a book-length reflection on the mysteries of our solar system, especially the intriguing case of Pluto. Known for helping reclassify Pluto as a dwarf planet, Tyson provides insightful commentary on the evolving field of celestial mechanics and the public's fascination with the overlooked corners of space. Pluto's reclassification is framed as part of our expanding knowledge of the solar system. Tyson views it not as a demotion, but a necessary shift in how we understand the many bodies orbiting our Sun. His approach to astrophysics emphasizes continuous learning and change. He recognizes Pluto's orbit and its interactions with Neptune as examples of space's inherent unpredictability. He proposes that while Pluto's orbit is currently stable, it may undergo significant changes in the future. Tyson's viewpoint isn't one of fear but of curiosity and scientific caution. It echoes a larger theme in modern astrophysics. Even systems that seem stable can experience unexpected shifts due to the finely tuned interactions of gravity, motion, and time. In Pluto's case, these forces are still being studied, debated, and tested through increasingly sophisticated simulations and observational data. Michio Kaku, another prominent voice in astrophysics, has also contributed to the discussion. Known for making complex scientific topics accessible to the public, Kaku shares Tyson's intrigue with Pluto's unique orbit. He emphasizes how Pluto's interaction with Neptune, while currently safe, exemplifies the fragile balance of celestial mechanics. According to Kaku, one of the most interesting aspects of the Pluto-Neptune relationship is how it illustrates the broader vulnerability of planetary systems to even the smallest disruptions. A comet, a rogue planet, or gravitational interference from a passing star could in theory disrupt the delicate balance that has kept Pluto's orbit stable for billions of years. While such events are rare, they're not impossible, and their consequences could ripple across the entire solar system. The possibility of a future Pluto-Neptune collision is not a forecast of doom, but a hypothetical scenario that showcases just how much we still have to learn about orbital stability and chaos theory in space. These what-ifs drive scientific progress. They force astronomers to refine models, improve measurement techniques, and better understand the hidden rules governing celestial motion. In recent years, space agencies and academic institutions have devoted significant computing power to simulate the long-term evolution of the solar system. These simulations show us that Pluto's orbit, while technically chaotic, behaves in a quasi-stable manner over billions of years. But they also reveal how sensitive this stability is. A shift in Neptune's mass, Pluto's speed, or even a small perturbation from another planet could eventually create enough deviation to threaten the current balance. Yet despite the uncertainties, there's a poetic consistency in how the solar system manages itself. The same gravity that could throw planets into disarray is also what keeps them in line. Pluto's resonance with Neptune is a beautiful example. Their synchronized dance ensures that even as they cross paths in orbit, they never meet physically. It's a silent cosmic choreography, billions of years in the making. For scientists and space enthusiasts alike, Pluto's story is more than just a curious orbital anomaly. It represents the ongoing journey of discovery in a universe governed by laws we are only beginning to fully understand. It reminds us that even the coldest, smallest bodies in the solar system can offer insights into the grander scheme of cosmic order. And as our telescope satellites and computer models grow ever more advanced, we continue to unravel the mysteries of these distant worlds, mysteries that could redefine how we see our place in the universe.